my God.
And I could barely breathe in this thing.
It's so funny. Can I take a picture? Can I take a picture of this? This is
Yeah,
so
go ahead. Front man wouldn't approve. Oh, okay. And I can barely breathe in that thing. Oh. All right, so I have that and this one. Okay. And shit. So, all right, and oh, as I get more oxygen to my bloodstream, so does anybody? Oh, a couple things I want to talk about. So I think you guys saw my email. I'm going to get my booster shot tomorrow, and the research says, or at least the research, the reports say that the people that have their third shots, they tend to have more site pain, but less systemic overall. So, but it's still pretty rough. So I'll probably be out of action on Friday. So hopefully that's it. So, and I'm doing it late on Thursday. So last time it took me about a day. I was out of the action and I was tired for another 2 days after that. So, but we'll see. It's great sleeping aid, by the way. So if you ever, I don't know, did you guys feel that way after your vaccines or? So, or did you guys go on? So did you, I don't know.
I had like really low effect. I mean, it was a slightly worse day.
Your days are already terrible. It's just,
sports, so I didn't have a choice.
yeah.
I went to work the day after and I was like, damn, it's because I was lifting all the tea. I thought I was just like fatigue being stored. Like, oh God, this is not, it's like saving.
Plus you got on your right arm. Yeah. So the other thing is, so I was tracking your guys' test scores, and about a third of you guys dropped down from the first test. So I'm a little, I always write the students, and I really want to see you guys through. I mean, what I mean is, like, I do feel compelled. It's terrible how low our graduation rate is in Maui College and also in STEM in general. I mean, 1/3 of students going through is just unacceptable. It's absolutely unacceptable. And Maui College, our graduation rate went from 15% to 21%. And that's it's the right direction. But like UH Manoa's graduation rate is 44%. And most,
They have money, so.
People like grab out or switch out?
what are you talking about?
Like why they don't have people graduating? It's just everybody drops out or?
In Maui College?
Yeah.
Yeah.
Oh. Oh, so if you like transfer, does that count as like dropping out?
No.
Okay.
Also timeliness too, right?
And what was that?
Timeliness too, does that count? Like
I'm not sure on that, because yeah, it is 3 years for an associate's degree. I'm not
Right,
entirely sure.
Yeah.
That could be part of it.
you could do it in theory if you summer school.
Because a lot of people just, they're just kind of busy, right? And they can't complete it all
Yeah.
in 1 year.
I actually think it could be something about the public school system and then the gap between college and school system. Like maybe the education's not good enough.
It could be. I don't know. Most of the colleges in the mainland, though, they're at 40 to 45%. So we're falling behind. But anyway, like I feel incumbent upon myself to raise those numbers up, at least for my own students, right? I mean, you guys are my own students, obviously. So, and I want to help you as much as I can. And you two Zoomers, this is the I don't know, is there a royal you? This is the plural you. So. And so, I mean, in general, if you need anything, and when I email you guys, you're never in trouble. I think I might even put, you're in trouble in the email, or maybe I'll start doing that just to mess with people.
All caps. Respond.
You have the one where it's like you're not in trouble. I saw that. I had a heart attack.
Well, I mean, yeah, but I see myself more as a coach, and I want you not only to do well in my class, I want you to do well in all your classes. Right. So it's not just chemistry, it's everything. So, and like I said, if I'm writing you, it's not you're in trouble. And if you need help, I mean, just anything, let me know. I'll do what I can to help. I'm not just, it's not my emails are more than just pretty pictures, right? So I do mean when I say, okay, fair enough. So now my eyes itch. It's mask. Ugh, all right. Anybody have any questions or anything? Are you feeling, yeah,
If you, did you want to talk about the test a little bit? Since you-
sure?
Well, personally, it was just, I think chapter 5 and chapter 6 was just a lot of content. And that's why, that was the part where I was lacking.
Okay, so oxidation states, well, I guess it was solutions, oxidation, there's a lot of stuff.
And I think ideal gas laws was in there too.
That was, yeah, the one, this test. That was the next chapter.
But then like all the thermodynamic stuff was easier.
Yeah, it's pretty straightforward.
Yeah.
No, and I mean, that's like people, another conversation. We weren't just talking about knives. I mean, one thing about chemistry is it's so many new topics. I mean, you get so many mental models, especially in Gen Chem 1. It's just, you come in and you have a new mental model. I mean, I guess not today, we're not gonna have a new mental model. Next class, we're having a new mental model. It's just, that's just the nature of it. So, and people hate this class, by the way. People absolutely hate this class. So I thought it was easy. Actually, I tested out of it, but I mean,
Tested out of it.
AP.
Oh, gotcha.
Subtle flex.
What's that?
Subtle flex.
Total flex. Yeah. No, I mean, I guess so. Yeah, I know it was just, I didn't have a lot of the struggles with chemistry. My parents are both chemists, and I'm the fourth generation of chemistry, it's just, I don't know.
Yeah, I mean,
Yeah, I had no choice, it's just like, what is this guy gonna be, I got my money on chemist. I even changed majors to become a chemist, I started off a different major, but no, I guess, I mean, I certainly struggled in grad school, but undergrad was easy, like especially chemistry. But anyways, I'm sorry. What's that?
So must be nice.
Yeah.
If you make me feel better, I'm only feeling your plus.
Okay.
Nah.
Ah, fine. Can we talk about chemistry then? Maybe the quantum mechanical model, perhaps? Does anybody have anything else they want to say? No? Okay. All righty. At least we had it all recorded. All right, so there's a couple classes. There's for 162, there's a class that's even worse than last class we had. And I feel for you guys. I mean, like there's two ways to look at this stuff. It's either like, what the heck, or it's, oh, cool. And when I remember I was learning about this stuff, I had the, oh, cool kind of feeling.
can we have like both? Like, oh, what the heck? This is cool.
There you go. There you go. It's all about framing, right? So, and hopefully this is going to make a little more sense this time around. And this is the quantum mechanical model, okay? And it actually, we have physical effects from it. We'll show you later on today a calculation that we'll do using this, and it turns out to actually, the model actually supports reality. So it's not just like, oh, this is some model, that doesn't mean anything. It does mean something. And Zoomers, can you see the screen, like the quantum numbers on it? Is that what you see? You can just put in the chat or put a thumbs up or something. Or do you just see me?
No, we see the quantum numbers.
Okay, good. All right. All right, so we're going to start with the principal quantum number. The principal quantum number is just whole numbers. Okay, so not zero, whole numbers, 1, 2, 3, 4, 5, 6, on to infinity, but whole number steps, not continuous mathematics where you have like 1.5 or something like that, just whole numbers. And so that's the first one. Once you set your principal quantum number, then you can set your angular momentum quantum number. And we call this little l. Little l is bound by 0 plus whole numbers up to the principal quantum number minus 1. So we set n, and then we set l, and l is bound by n. And then m sub l, the magnetic quantum number, is bound by the angular momentum quantum number l. M sub l is bound by integers. And it goes from minus l integer steps, including 0, up to positive l. And then the last one, which is not in this chapter, is the spin, but I'm telling it now because it makes more sense. So the spin for an electron is either +1/2 or -1/2. And also, aforementioned last time, for L, we give names for angular momentum. These build things called orbitals. And for when the L is 0, we call that an S orbital. When L is 1, that's a P. L is 2, that's a D. L is 3, that's an F. And after that, we just go alphabetical G, H, I, J, K, L. But that's, in this class, you wouldn't really have to worry about that. There are higher orbitals. It's just we specifically name the ones up to 3. And we do label them with, I guess it's D, or we actually, I guess what are they doing? Nuclear chem. I guess they do label them with letters in nuclear chem. Because nuclei also, protons and neutrons have orbitals too. But okay, so, and next chapter, we'll talk about this, the Pauli exclusion principle. So no two fermions, electrons are fermions. No two fermions may have the same set of quantum numbers in the same atom, which means you can only fit 2 electrons in each orbital, because one can be +1/2, one can be -1/2 to the spin. So, and also mention the so what with this, among other things, is matter has structure. So there's lots of things that have structure. Space-time has structure, matter has structure. Energy itself has structure, but energy combined has no structure. So if you throw a bunch of energy together, it doesn't form anything. You throw a bunch of matter together, it forms something that has structure. Whereas energy, right? I mean, there's energy passing through me right now. It doesn't do, I mean, it can interact with matter, but you put as much energy as you want in a certain location, it's not going to do anything. And energy itself has structure, but the bunch of energy together doesn't have structure. Yeah.
So you can put an infinite amount of energy in a finite space.
Yes.
So like a black hole too.
Well, black hole is a singularity, which is infinite density. I was thinking more of the Big Bang, but
So it's mass, not energy.
it could be interchangeable. That's this one that we don't know.
Yeah, that's right.
Yeah. Gravity is stronger than the speed of light in that area, and that we know that. But as far as what happens beyond the event horizon, that's a little bit difficult. So, other questions? It seems like information is conserved, though, if you want to look more into that. Okay, so let's do some quantum numbers. Is this making more sense now? Is it less scary? I told you it would be. Ha ha. You'll listen to me more.
I don't really understand the Pauli exclusion principle, like, because aren't there multiple electrons, like more than 2 electrons in an orbital? I mean, or, yeah, right?
In an orbital, there can only be 2.
Oh, what is the orbital?
We're kind of going to get to that coming up. So do you mind holding, and especially in chapter 9 is periodic trends, and we talk about orbitals filling up. Do you mind holding your question? Like, I mean, I can certainly answer your question, but we're also building up to it. So, I guess what was your question? Whether what are orbitals? Orbitals are they're things defined by 3 quantum numbers. So like n equals 1, L equals 0, M sub L equals 0. That's an orbital.
That's the first one.
This is the 1s orbital, and you can only fit 2 electrons in that.
Do those numbers help us determine where an electron is?
Yes.
Okay.
So like the amount of quantum numbers there are is an orbital. Like, so if it's like if n equals 2, then it'll change the L and the M to L.
Yes. Well, I mean, if n equals 2, so let's follow this. If n equals 2, L can be 0 or L can be 1. Then M sub L equals 0. M sub L can be -1, 0, or 1. And so this is the 1s orbital. This is the I'm sorry, that's not the 1s, this is 2s. This is the 2s, this is the 2p x, 2p y, 2p z. Actually, I'm not sure which orient is what, but I mean, it's just you have 3 orbitals. So you have 1 orbital here, you have 3 orbitals there. And each orbital can fit 2 electrons.
One spinning up, one spinning
Yeah,
out.
this is plus 1/2. This is minus 1/2. This is the ms, the spin. So that's what we're building up to. So does that answer your question?
We did
Okay.
the thing diagrams, we did do that for that. for this
Yeah.
one.
Yeah, I understand like the, like filling up the orbitals and even relating it to the periodic table and trends and stuff. I don't understand like why I follow those rules or anything. They're hard for me.
Because some scientists said so.
Because yeah. Well, I mean, so first of all, chemistry is an observational science. You know, we're only reporting what we're seeing. You know, it's not like something like, joke's on you folks. You know, it's all imaginary. You know, I mean, and this is also the quantum mechanical model, so we can, you know, it's how we model it. But I mean, we do see effects. I mean, it's not like we do this and it's like completely blown away. There's a huge disconnect between reality and this model. It's a pretty solid model, right? So there, it's not like I'm gonna come to class. And besides, I try to tell you the truth as much as I can. So I'm not gonna be like, oh, you can learn more about it later. You know, I'm probably blowing your minds away talking about the complex conjugate of the integral and stuff like that. But yeah. Anyways, so we'll hopefully you'll get more as we build up more and more. So, or do you have any follow-up questions or? Okay, so let me go back and do this problem. And so we have, what are the quantum numbers and names of the orbitals in n equals 4 principal quantum numbers? And how many n equals 4 orbitals exist? So n equals 4. So that means L can be 0, 1, 2, or 3. And that means M sub L is bound by, and so L can be 0 up to n minus 1. So 0, 1, 2, 3. M sub L is bound by minus L to positive L by integer steps. So M sub L can only be 0 for when L is 0. For 1, it can be minus 1, 0, or 1. For 2, it can be minus 2, minus 1, 0, 1, and 2. And for 3, it can be minus 3, minus 2, minus 1, 0, 1, 2, 3, 4. And these orbitals, this is known as the 4s. These are known as the 4p's. These are the 4Ds, and these are the 4F orbitals.
It goes down to 4. I thought it stopped at 3.
You're right. I got too excited because it was 4F, and you're right. Okay. You're right. That's not an exception. Okay. So how many n equal 4 orbitals exist? So it's going to be 1 plus 3 plus 5 plus 7. So that's what, 8 times 2, 16 orbitals. And which also implies you can fit 32 electrons in the orbital. And why did I put 32 electrons? Why do we care? This is something from, and actually Rihanna came up and talked to me after class about it. We don't even cover something called the Bohr model. So you ever heard, maybe you've seen this before. So the Bohr model, where you have something like you have the nucleus and then you have 2 electrons and then you have 8 electrons. And it looks like this. Have you seen something like that before? That's known as the Bohr model. And you have the different shells. And you have, so it's 2n squared. N is still the principal quantum number. So the first shell can fit 2 electrons. So n equals 1 means 2 electrons. N equals 2 is going to be 2 squared, 2 times 2 squared, which is 8 electrons. And then n equals 3 is going to be 2 times 3 squared. So that's 18 electrons. And then 32 for, oh geez. I already mentioned it'll be 32 for n equals 4 and so on. So actually the quantum mechanical model matches up very well with the Bohr model for certain things. And like the Bohr model, atoms are layered. They're like ogres, they're like onions, right? So from the Shrek fans. So we have different shells. So we'll get to that. So how are we doing so far? Questions? Please.
Sorry, where did you get the 1 plus 3 plus 5 plus 7? I understand the 16 orbitals and the 32 electrons, but where did you get the 1 plus 16?
One orbital. Three orbitals. Five orbitals.
Thank you.
Yeah. So yeah, no worries. Sorry if I'm bringing Sesame Street into this. Other questions? Oh, okay. Frontman says so. Okay. So here are some sets of quantum numbers that specify an orbital. One set is erroneous. Which one and why? So let's go through the logic, and I'll start with A. So if n equals 3, L can be, so 0, 1, 2. 0 is okay. If L is 0, M sub L can only be 0. A is okay. So B, n equals 2, L can be 0 or 1. 1 is fine. If L is 1, M sub L can be -1, 0, or 1. -1 is fine. B is okay. So for C, when L equals 1, I'm sorry, when n equals 1, L has to be 0. There's no other choice. If L is 0, M sub L has to be 0. So this is actually fine. That's only one orbital allowed at n equals 1. And then we get to D, and if n equals 4, L can be 0, 1, 2, or 3. So L equals 1 is fine. If L is 1, M sub L can be -1, 0, 1. M sub L being -2 is not possible because of this L. Therefore, this is the one that's erroneous. So does that make sense? Okay. So let's see, you can follow. Which set of quantum numbers here is erroneous? And each of these would describe an orbital, so. So how many think A is wrong, or I'll say folly? Which one is folly? Is A folly? How about B? Is B folly? How about C? How about D? All right, so everyone's going for D. All right, yes, you're correct. If L is 1, M sub L can be, it's fine to have L as 1 if N is 4, but M sub L has to be -1, 0, or 1. So questions. So, okay. So let's change topics to something a little more like colloquial. Let's say you're hosting a party and it's a movie party, which actually I did recently. Say you're watching Dune, or what do you guys want to watch? Squid Game, Dune, what movie? What, you want Squid Game? Okay, we're gonna watch a Squid Game party. Okay, and so at this party, you have a television, and right in front of the television, you have a nice easy chair. So put your feet up. Behind that, you have a comfy couch. Behind that, you have a wooden chair. And then behind that, you have standing room. So if you're the first one of the party, so I'm pink. If you're the first one of the party, where are you going to go? That's right. You're going to plop down that easy chair. Right. So
Can you fit your girlfriend in there or your wife?
We're just gonna sit with single people for now. So socially distance, of course, it's COVID, right?
Cool.
So then the next one that fills up, will probably be the couch. So you can fit more people on the couch. Then, crappy chair. So what's gonna happen? What's going to happen if the guy in the easy chair or gal, I don't know, whatever, we're open to all genders, of course. What's going to happen? I'll say, how about the person? That for a second. What if the person in the front row in the easy chair? What's going to happen if that person gets up to go to the bathroom? Yes, someone's going to take their spot. And what are you going to do after you've been sitting in an uncomfortable chair and you finally sit in the lazy boy easy chair? What are you going to do? Yeah, make popcorn. Well, then it leaves the seat open. Yeah, you're going to go, I'm so relaxed, right? You're going to relax down, sink into that chair. Okay. So what if instead of a television, we had a nucleus? The nucleus is positively charged, right? And we have negative electrons. And instead of chairs, we have set orbitals. So of course, first one of the party is going to sit down. And so let's talk about sitting up. So of course, the orbital, which is closest to the nucleus, this is the lowest energy because you're a negative electron and there's a positive nucleus. So the closer unlike charges are, the more attraction they feel. That's Coulomb's law. You probably know that already, or the concept of that, right? So opposite charges attract, and also, although this is magnetism, it's different than electronic fields, but like when you have magnets that are close together, it's harder to pull them apart. So the closer you are, the stronger the force. So if you have an electron there in the ground state, the lowest energy state, and you can then promote this up to a higher energy state. And anybody want to guess what the promotion is called? It's called excitation, right? So here I am, I'm sitting down, I'm low energy, and now excitation, I'm excited, I'm higher energy. And then when you go back down, that is called relaxation, right? So this is excitation, and then from this state, it can go to either down one. This is called relaxation. So it goes down in energy. And when it goes, but you can see there's two energy steps. So when it goes down in energy, though, the electrons drop down in energy. And then what do? They release a photon, equivalent to the energy change. And that's for the low energy. And then for the bigger step, high energy. So when you have electrons going up and down in energy levels, they will absorb and emit energy, and commonly done as a way to emit energy is to emit photons. And if you've noticed, I've put red for the low step and green for the bigger step, because green is higher energy than red. So the light coming off will do that. So yeah, question.
When it jumps and it excites, does it absorb an energy?
Yes.
Okay.
It can from a photon. So you can excite by photons, by heat. If you heat something up enough, it'll excite. Chemical reaction as another way. Oh, an electronic discharge. So you can hit it with a bolt of lightning. So like these are fluorescent lights, and in them is mercury, and the mercury is excited. So the way that these fluorescent, so sorry, Zoomers, we're in a classroom. You have, So for the fluorescent lights, the way they work, you have an excitation up to a really high state, and then when it relaxes back down. So as this one relaxes back down, it emits a UV photon. So, and then if you look on the edges of the light, it looks white. It's that's phosphorus oxide. So the UV light hits the phosphorus oxide and it makes it fluoresce from the ultraviolet light from the mercury. So that's why they're called fluorescent lights. So it's mercury and phosphorus causes the light to come. But anyway, so that's how you do excitation. So excitation, relaxation. So, and atoms and electrons are a lot like people. So if I told you, I want you to do something, you have to do the same thing for the next 5 hours, what would you pick to do for the next 5 hours? Sleep, relax. Who wants to do jumping jacks for 5 hours? You know, who wants to do push-ups, right? So people, if you're going to be doing something for a long time, they're going to want to choose to be low energy, right? So no one's going to be like, you know, I mean, there are people who do marathons, you know, that's cool, you know, but generally speaking, if you're going to be doing something for a long time, you choose a relaxed state. Same thing with electrons, right? So, and if you have slots, like I have here with the, with our Squid Game party, right? I mean, in the chair, I even mentioned standing room, right? If you're standing up, that takes energy, but it's, you know, it's not too bad. Sitting down, like I'm sitting down now, you know, I'm activating my core, you know, I'm keeping my spine up, right? It takes energy, right? If all of a sudden I lose consciousness, right, I'm just gonna, like, I'll fall back, you know, kind of thing. It takes energy to stay, you know, upright. Couches is a little less, right? You can just sit in the cushions. And easy chair, right? You are hit my head on the thing. Keep on hitting again. Hit my head a few times, I really will pass out. You know, easy chair, you're just totally relaxed, kind of thing, right? So, and just like people, just like electrons, we like to be low energy. And so if that slot opens up, you know, we're going to take it. We're going to take the easy chair. Yeah.
So I'm trying to like find ways to like grasp it. So orbitals and shells are kind of like the same thing almost, but shells can hold more electrons than orbitals.
Shells are defined by the principal quantum number. So that's a leftover from the Bohr model. So the Bohr model works for hydrogen and or hydrogen-like atoms, meaning you have a single electron. So when you get more than one electron, the electrons have magnetic and electronic fields and they just mess everything up. So we'll get into that next chapter.
Okay, sorry, because you mentioned the Bohr model.
Yeah. 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 The Bohr model, we don't even cover it. So I only mentioned it because Rihanna asked about it. So sorry if I'm putting it in the spot. I mean, it's great. It's great that you learned the Bohr model. It's a good model. It works really well, but it doesn't work it's not as good as the quantum mechanical model. So, all right. And other things. So visible light, this is what visible light does. Visible light causes excitations and relaxations emit visible light. That's what visible light does in the electromagnetic spectrum. We started off this chapter talking about the electromagnetic spectrum. So ultraviolet light. So the ultraviolet light is an ionizing radiation. So if you were at our party and, you know, I don't know what a bouncer man will look like, we'll give him muscles, and there's a hand. Here's my bouncer. That looks like a scary bouncer. So fine, we'll give him a pirate hat. So there's my bouncer, and let's say this person is no longer welcome at the party. So what the bouncer can do is can take this person and, you know, push them out the door, right? So person's in the back, it's going to be easy. Bouncer opens the back door, shoves the person out, closes the door, ha ha ha, right? That's what ultraviolet light does. Ultraviolet light, it goes for the surface electrons, also known as the valence. So ultraviolet light will ionize valence electrons. X-rays though can go and kick people out further in. So like say the person sitting in the chair was really bothering me. If this was the UV photon, right? Because someone in the back of the party, it's pretty easy just to shove the person out. To get the person off the chair, you have to pick the person up off the chair, lumber over and throw the person out the front door or something, or back door, It's a lot harder to do. So same thing, you just need to have, we'll give this bigger muscles. So this would be an X-ray. An X-ray is just like the bouncer, but more jacked up. So the X-ray can have enough energy to rip the person off of the easy chair and throw that person out of the house. So, and the X-rays, of course, can still get the surface ones. So the X-rays just have the added ability of getting all of them, including the core, the inner electrons. So, but we tend not to focus on that as much. We're going to look mostly at the visible light for now. So, questions so far? All right, so here's the picture that I tried to talk about with the party. And so the y-axis here, this is in the top image, this is potential energy. So remember, free electrons have 0 potential energy and bound electrons have negative. So this in the n=1 state has the most negative potential energy. And then 2 slightly less, 3 slightly less. And these are the different states. So absorb energy, that's excitation, up in energy, and then relaxation goes down. Excitation, relaxation. And here's the numbers. The change in energy is the final minus initial. It's this Rydberg constant, which is 2.18 times 10 to the minus 18 joules. And that's for the hydrogen atom. So hydrogen atom, and the negative because it's negative potential energy. And then the final minus initial, everything is always final minus initial for change. And I'll show you. Oh, you want to zoom in? Here you go. So here's the equation that we'll use. Energy change is minus the Rydberg constant times the quantity 1 over the final quantum number minus 1 over the initial quantum number is the energy change. And don't worry, we'll see you write it down. You get all the equations. Okay. So this is, like I said, for hydrogen atom. And here is the hydrogen atom, at least the spectra for it. So the n=infinity level, again, the y-axis implied is potential energy. So n=1 is the lowest energy, and then all the way up to n=infinity. So ionization, that's when the electron is ripped out of the atom. And so the n=1 level, when you have electrons going from any level down to the n=1 level, this is known as the Lyman series. Did you talk about that at all in astronomy?
A little, yeah.
Yeah, this is the Lyman series. And then the visible light for coming down, that's called the Balmer series. So if you ever see Lyman series, Balmer series. And then the other one, these are infrared. So you can get infrared, it's not just heat, not just vibration. You can get it from electronic excitation, deexcitation kind of stuff. But infrared in general, though, is heat. Okay, so this is the visible wavelengths. And actually, hydrogen, so we don't have prisms in our eyes. I guess we could, but our brain just interprets signals as one. So actually, if you look at the hydrogen spectra, it looks pink to my eyes. About the color of my shirt, kind of a fuchsia. This is supposedly watermelon, is what the Amazon said the color of this was. It's kind of a fuchsia, like a purpley pink color to my eyes. I can't tell you what it's gonna look for your eyes. So, but our eyes work differently than spectrometers. Okay, so let's do this. So determine the wavelength of light emitted when a hydrogen makes a transition from the n=5 to n=6 level. So it's Rydberg, the change in energy is, well, the change in energy is final minus initial. I know I had the minus one. I guess you didn't need the negative sign here. Let me see. Anyways, oh, I see the change in energy. It loses energy. Yes. It's going to lose. Yeah, n=6, n=5. It's going to the energy of the photon is going to be minus the energy of the electron. The electron is losing energy, but then the photon gains energy. So that's the reason why we have a positive sign there. So if that means anything. But let me change colors. I like writing in blue. So we have the Rydberg, so say delta E is Rydberg constant. So 1/5 squared minus 1/6 squared. So R infinity 1/25 minus 1/36. So, and then you just plug in the numbers. Delta E equals 2.18 times 10 to the minus 18 joules times the quantity 1/25 minus 1/36. So, and by numbers, so whenever I look at a fraction like this, so 1/25, 25 is a smaller number than 36. This, to me, this quantity here, this is a positive quantity. So I'm expecting to get a positive number in my calculator, right? So 1/25 minus 1/36. What I mean, like, what is 1/2 minus 1/9, for instance, right? So the 1/9 is, 9 is a bigger number than 2, but 1/2 is a bigger number than 1/9. So 1/2 minus 1/9 is a positive number, right? So I'm going to expect a positive number. Let me put this. Oh. Let me cheat and look in the book. Ooh, I came right there. So this is going to be, delta E is going to be 2.66 times 10 to the minus 20 joules. So if you put that in there. And what does it want? It wants this wavelength. So this is energy. And specifically, it's the energy of the photon. So the energy of the electron, the energy delta E electron, this is going to be minus 2.66 times 10 to the minus 20 joule. And that generates a photon energy, which is positive 2.66 times 10 to the minus 20 joules. So if that makes sense, where the energy is going, because energy is conserved. And then
Been divided by speed of light.
yeah, well, energy is equal to h nu, which is equal to hc over lambda. Remember that? So because lambda, so c equals lambda nu. So that means nu is c over lambda. And you can then solve for lambda. Lambda is equal to hc over e. So are you guys following all that math, or am anybody confused? Now's the time to ask. Did I go over it too quickly? Nope. Okay. So then h doesn't change. 6.626 times 10 to the minus 34 joule seconds. C is 3 times 10 to the 8 meters per second. That's an ugly 8. And then energy is going to be 2.66 times 10 to the minus 20 joules. So unit wise, joules cancel, seconds cancel, and we're left with meters. So our lambda equals 7.46 times 10 to the minus 6 meters, or multiply by 10 to the 9, and you get 7460 nanometers. So however you want to look at this. Okay. So why do students hate this problem? Because it combines two topics together, right? And so we have the Rydberg numbers. So we have the energy levels are defined by minus 1 over n squared. So a bound electron has negative potential energy. So the change in energy is always final minus initial. And so when we have energy change, we have final minus initial. So if n equals, so it goes from 6 to 5, initial is 6, final is 5, it loses energy. The electron loses energy. So it's, what should I say, it loses potential energy, has more negative potential energy. So final 5, initial 6, squared 1 over 25 minus 1 over 36, multiplied by the Rydberg constant. And we do that, we get 2.66 times 10 to the minus 20 joules. So the electron loses this much energy. The energy loss of the electron is equal to the energy gain that's going to turn into a single photon. So that photon that the electron loses from relaxing down is this amount of energy. And solving, so energy is h times frequency, also, or h speed of light divided by the wavelength. So wavelength is then Planck's constant, speed of light over the energy of the photon. We do that and we get 7,460 nanometers, or 7.46 times 10 to the minus 6 meters. So you have to do 2 steps with this problem, or 3 if you want to do the energetics. We consider the energetics a step. So how are we doing? So questions?
I got a 9 instead of a 7 for the wavelength.
All right. Did you get 2.66 times 10 to the minus 20 joules?
Yeah.
All right. Let me check.
Probably just in my computer or calculator instrumentation. It's harder with this.
Hey, this calculators are free. I'm getting 7473 nanometers. I guess maybe the book didn't round going up, but yeah, I'm in the same neighborhood. Here's mine. Exponent. The E button.
Okay, I use 10x and it like makes it difficult. So I just use E.
Yeah, I would just use E.
Okay.
So, other questions? All right, I'm not going to make you do the rest of the calculations, but so tell me about the energy of the photon emitted as it goes from the well, I should say, I guess it backwards, the n equals 1 to n equals 3 to n equals 1. Yeah, so it goes from 3 to 1. What's the energy of it coming out? And I'm just putting the Rydberg. You don't have to do the wavelength. You just have to do the Rydberg.
Why is the time changing it?
So the electron loses energy. The sign change is negative because the electron loses energy. but the energy loss of the electron is equal, it's going to turn into a positive energy of the photon. Does that make sense? Right, kind of like when you grab something cold, I can feel this is cold. The cold object, the energy is in the positive direction. Energy for me is a negative direction. So when electrons go from excitation to relaxation, they relax, they release energy, and that their energy is negative, they're going down. The energy then, the photon popping off is then positive. Well, it has to be, there's no such thing as negative energy. Well, direction, but there's no negative, like antiphotons or something like that. Have you guys ever seen Hot Fuzz?
I have.
Yeah. Whenever someone asks me that, I always want to ask me a question. I always want to say NARP. YARP.
Gruesome movie.
So how many people think A? How many think B? How many think C? Okay, everyone's going for C. C is correct. So do you see it? It's final squared is 1 over 1, and initial is 3. So 1 minus 1/9. 1 can also be written as 9/9. So 9/9 minus 1/9 is 8/9. So I really didn't want to do, I didn't do the fractions for this one because 5 is a prime number and 6 is 2 times 3. So it's going to be 25 times 36, whatever that is. Well, it's going to be 11 divided by 25 over 36, which is another prime number. So many prime numbers. So anyways, anybody got any questions with this? Is it making sense? Is this getting more palatable for you guys? Okay. So orbital shapes. So we talked briefly about orbital shapes. And then I mentioned this before, what you do for them. So remember the wave function, you have the Hamiltonian operator, which is the kinetic and potential energy of the electron, operates on the wave function, get the energy levels out. And if you take the wave function times its complex conjugate, which is the vector dot product. You haven't studied linear algebra yet, I don't think. Right, so. Nah, it's beyond that. Maybe you've seen a complex number like that, 3 plus 2i. The complex conjugate is the opposite sign of the imaginary portion. So, and it's also the vector dot product. When you study linear algebra, you have columns and you line them up certain ways and you multiply them. And then you integrate d tau. It's going to be dx, dy, dz. Or did you guys have you studied other coordinate systems yet? The like, you have d theta, d phi, dr, I forget the order, maybe it's dr, d theta, I don't know. The spherical coordinates or radial, you haven't done that? Okay. There's other ways to do it as well, but you have the Cartesian coordinates. This is Cartesian, René Descartes. It's the box one. You have radial. Radial is, you have this angle, you have the radius, and then you have z. So you have like a series of circles. And then there's spherical, where you have this angle, you have this angle, and then you have the radius. So, but you can learn about that when you follow more into calculus. I guess sometimes I teach radial and I learned about radial at least in pre-calc. Or did you not do radial? Okay. All right. Anyways, it's all space, integrate over all space. Integral, what is an integral? It's the area underneath the curve. But let's talk about the different ones. So let's talk about the 1s orbital. This is easy. The 1s orbital, and you look at the probability, the density of the dots is proportional to the psi dot psi squared. And then you look at the probability density and it approaches infinity at the origin. So, but then what you do is you look at the radius. So this is this psi squared, that's that part. But then when you integrate it over the area, so what do I mean by integrate? So you have a probability density, and it's very probable to find it at the origin. But it's when you integrate something, you look at it in layers, look at tiny slices. And I'm saying atoms are like onions, right? So when you cut open an onion, you get a small onion, then a bigger onion, or kind of like those Russian dolls. I forget what they're called. You know what I'm talking about? Okay, sure. I believe anything you say at this point in time. You said bambushka? Mantushka, okay. I thought bambushka was grandma. Okay. Yeah, okay. So this is the actual radial distance, radial distribution function. And so this is the 1s electron. And so this is where we actually find it. And you can see here, like basically at like 250 picometers. So pico is 10 to the minus 15. So at about 250-ish, 300 picometers, you don't see the electron after that. So, I mean, I mentioned before, like, oh, so that means the wave function for my 1s electron is also in Jupiter. It's in the sun. It is, but practically it doesn't exist there. So, but one thing about the 1s electron, notice something, the atom's nucleus is finite in size here. So one of the so what's in this, I didn't draw that line very well, had it better in the other one. One of the so what's in this is, this then tells you that the electrons can exist into the atom's nucleus. And electrons actually do exist in atoms' nuclei. So this is another thing you probably learned in high school, like, oh, the electron cloud is outside of the nucleus. And here I am in college, you know, and guess what? Electrons can be in the nucleus too. So not very much. Question?
Does it ever bond with the proton?
Well, not at all. So the electron is uncertain. Here is it's a cloud. So meaning you kind of have, if you're gonna do a slice, you have a little bit here, but then you have like kind of a maximum at a certain distance, and then it tails off. So I didn't draw that very well, shoot. So, well, if you look at this, there's actually kind of like about right here is where the electron has the most density. So it doesn't necessarily bond with the nucleus because the electron, remember, has uncertainty position. You have the uncertainty, which is delta x, delta p is going to be greater than or equal to h over 4 pi. So because of the uncertainty, the electron is actually in all these, I was talking to the iPad, sorry. The electron is in all these places at the same time. It's uncertain where its position is. So, which means, practically speaking, it's everywhere. It has a Coulombic attraction. It doesn't bond with the protons, because if it bonds with the proton, it'll no longer have the cloud. I guess it can. You can have, there's a type of radiation called electron capture. It used to be called K capture. So if the electron does, it can bond with a proton to form a neutron. And that's a specific type of radioactive decay. It's called electron capture or Kern capture, because Kern, I guess, is first or something like that in German. K capture, electron capture. That's a very rare case, though.
Would it be a heavy element for that to happen probably?
No, you can do it. It's
Oh,
a.
like carbon.
I don't think carbon does K capture. I have to look at my nuclear chemistry. I don't remember, to be honest with you. It depends on the. It might, because I think carbon tends to do more positron emission. There's a lot of different radioactive decay series that have similar energy or similar effects. So, because a K capture, sorry, I'm using the old term, the electron capture and the positron emission, because that's how PET scans work. You put carbon 10 in your when sugar and images where it is in your brain.
Okay.
So that's positron emission. Because positron emission and electron capture the same. It's hard to tell which one's going to happen. So, okay. Well, above and beyond this class, though, there's an electron. There's also a heavier particle called a muon, and muons are more massive than electrons. And muons have much more, because and they're like a muonic cloud versus electronic cloud, it's much smaller, and the muons spend more time in the nucleus of an atom. So we look at muons to study this effect, actually. The other thing is, isotopes, so same number of protons, different number of neutrons. The isotopes, they have almost exactly the same electron energy levels, but they change ever so slightly because of the electron density of the electron cloud in the nucleus. But where you see the most pronounced effect for this is the hydrogen atom. And the hydrogen atom is the only one we name the different isotopes. So hydrogen, normal hydrogen, we call it protium. Heavy hydrogen, we call deuterium. Radioactive hydrogen, we call it tritium. So, but we do see a little bit more of electronic effects there, but most of the other elements, though, it doesn't matter. So this is just kind of a side point. So, any questions? You look like you're formulating one. Yeah.
Oh, no.
Okay. So more things. So you have nodes. So quantum mechanics. So we have different quanta. And the reason why we have quantum mechanics, how it works is, well, whenever you have boundary conditions, you're going to have quantum effects. So there's quantum effects and things like there's this toy, I forget what it's called. It's like just a plastic tube. You turn it and it goes, roar, 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 and you spin it really fast. It goes, roar, 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 and then, roar, roar, roar. I can't, my voice can get that high. But right, you can spin it and it changes the frequency. And the reason why it does that, because you have a tube of a set length and you get sound waves going through. If it gets enough energy, it actually changes the pitch, and it only changes the pitch in a certain amount. And this for other things like pianos, right? So pianos or strings on string instruments, that kind of thing. When you change the length, when you're playing a violin or guitar, if you change the string lengths, you get different sounds coming off, right? But the sounds are constant, right? Whatever notes should always be the same, coming from whatever instrument you have, and that's actually a quantum effect. It's not a quantum mechanical effect, but it comes from boundary conditions. And although for musical instruments, we usually only use the first node for it, we don't go to an excited node. Electrons can go higher. So another one is, imagine a jump rope. So say that I took a rope and I attached it to the wall, and I started spinning it really hard with my arm. I'm going to have the first energy level. And if I keep on going, I keep on spinning it hard enough, I can get to form 2 lobes, right? And so this other lobe is a node. We have an area of 0 density. And so you can describe doing like using a jump rope or a rope and going against the wall and spinning it. You can use the quantum mechanical model if you want. This would be the principal n equals 1 level. This would be the n equals 2 level with 1 node. And then this one here, this picture. So a vibrating string, you have the different, so sorry, I'm talking to my iPad again. You have these different levels here. So this would be the n equals 4. That would be the n equals 4 level because you have the 3 nodes. So the same thing happens with electrons. So here is the 1s or the 2s and the 3s orbitals. So here is the 2s and the probability. And then now if you do the radial probability, total probability, you get a small lobe here and a bigger lobe here. And you actually have a region of 0 density. That's called a node. And this is also kind of weird. I think it's also cool. The electrons, where are the electrons? They are both here and here at the same time. But they are not here. They are not the nodes, but it's the same electron. And the electron is in certain places, is not in other places, all at the same time, because we have uncertainty in the position. And the same thing then, if you look at the n equals 3, you have 2 nodes. So the n equals 2, you have 1 node. N equals 3, you have 2 nodes. You have n minus 1 nodes. And but the electron, it kind of mostly hangs out here. So you can kind of see it with the image. I mean, like it's kind of darkest around right here. So that's where the electron spends most of its time. Same thing here. You can see that there's the 2 places here, but the electron mostly kind of hangs out here. But the electron is actually here, it's also here, it's also here, all at the same time. And one thing to note, kind of also outside this class for now, but if you see the 1s orbital, I'm sorry, the 2s orbital, you have this lobe here and this one here, the other one here. This is a phenomenon known as penetration, because the s orbitals, they will penetrate further in, because later on we'll talk about shielding. Not so much in this class, but if you look at this, if you have the outside electrons, you have the nucleus in the center, and then you have layers of shells of electrons. The outside electrons they're shielded by the other layers. So like this electron doesn't necessarily see the full positive charge of the nucleus, but an s orbital, because it has these lobes here, we say it penetrates through the core electrons and actually can feel more of the charge of the nucleus. So that's another thing. Okay, questions so far? All right, so here are the p orbitals. P means principal, not perpendicular. But one thing, and these are the 2 p's. So if you look at the 2 p's though, unlike the s orbital, there's a node at the origin. So a node area of 0 density. And the 0 density there means that the p orbitals, or the p electrons, they don't have very much density, or basically none at all, in the nucleus of the atom. So it's really the s orbital, specifically the 1s orbital, because at least for electronic atoms. Muonic atoms, there's more. The electronic atoms, the p orbitals, are not really affected by nuclear effects, where the s orbitals are, especially the 1s. But the p's are just oriented on different axes, x, y, and z. So where you have they're just oriented and just so happens to be perpendicular to each other in the x, y, z axis, or x, y, z if you're in Canada or Europe. So Here are the p orbitals. And one thing we haven't really mentioned, it's going to come important later when we talk about bonding. So there are signs to the wave functions. So because when you square it, remember you have the psi squared, and when you square any number, you get rid of the negatives, right? So when you have the actual wave function, you get areas, where you get, you have a change of sign. So you have a positive lobe and a negative lobe. And this is going to come important later when we talk about bonding, like I said. So because the orbitals, we're going to bond and they're going to form new orbitals, and how they overlap and whatnot is important. So let's move on and talk about d orbitals. I always thought this was cool. So we have, and these are the 3Ds. So specifically, these are the 3D orbitals, and you have 5 of them. So these are just in the plane. So the XY. So reading this, you have the XYZ Cartesian coordinate system, the DYZ. So that's this one. It's the plane flat to the screen, and you have a cloverleaf shape then with this orbital. And same thing with the DXZ. So that would be this one. So XZ. So X. So this is the Z axis. This is the Y axis, and then this is the X axis. So the DXZ is this plane. So perpendicular to the board and this direction. I mean, I know they're all perpendicular to each other, but it's perpendicular this way, similar cloverleaf. And then DXZ, I'm sorry, DXY, I'm sorry, it's this one. This is the DXZ, I didn't see that. This is the DXZ. This is the DXY. It's this one, perpendicular this way. This one is perpendicular this way. And then you have the dx squared minus y squared. These fall along the x and y axes. And then you have finally the dz square orbital, where it aligns mostly along the z axis. And all of these are called degenerate. So at least they're all the same energy. Degenerate means same energy. It means similar. It's actually kind of an insult for us right now. If I said you're a bunch of degenerates, you're all working hard on chemistry, you're all the same, you're just degenerates. So, right, these electrons, they're all the same energy. They're degenerate orbitals. And there is something called the Jahn-Teller effect, and where you see this in especially copper. For this one here, copper tends to form octahedral shapes. So an octahedron it's like, I don't know, well, hard to describe. If you, it looks kind of like a diamond. Fluorite has an octahedral geometry. It's like 2 square pyramids on top of each other. And what happens is the copper complex will actually extend along the z-axis, and that's because of that orbital. So it's not like this is just some crazy math trick. We actually see effects from that. So it's kind of cool. That's you don't learn about that till your junior year if you're a chemistry major. Here are the f orbitals. They're just all goofy looking. Right, so, yep. And I got 1 minute left. I already mentioned the phase of orbitals. So the s orbitals, they have only positive, but the p can have positive and negative. What's just the ones, well, the 1s has only positive. So what about atoms are spherical? Why are atoms mostly spherical? Well, let's draw this. Let's see here. Here we have the 1s orbital. Now let me draw the different p orbitals. Now let me do the d orbitals. So you got the one in this plane, then you got the one this plane there, and then the side plane. Then you have the along the axes, front and back, and then you have the dz squared there. And then you have the f's, which are just all over the place. But the idea is, you can see that at least the electronic, at least where the electrons are, when the electron's gonna have forces expelled, like around it, is gonna be roughly spherical. It's not perfectly spherical, but it's roughly spherical. So anyways, okay, so that's my shut up alarm. So I'll stop talking.